Hi guys. I wanted to make a video for you about one of the calculator questions because I'm feeling a little guilt for having spent zero time on the calculator, and because it turns out this is a particularly evil question. So the question this video will be about, and hopefully you can see this, is question 17 on practice midterm 1. It says the graphs of the functions f of x equals 5 plus x to the fourth and g of x equals 5 times 3 to the 0.2x intersect, and it asks how many times these functions intersect. Now, one thing you'll notice is that this is an exponential function because it has the x in the exponent. We haven't officially studied these functions yet, but in theory, the idea of this question is that you shouldn't really need to know about exponential functions, but you'll see why this is in fact a trickier question than I thought. So, okay, so the first thing you do when you see a question like this on calculator section of part of midterm 1 is pull out your calculator and graph the two functions. So I'm going to do that. Alright, hopefully you can see here. Turn on my calculator. My calculator goes into icon land when I turn it on, right? So you can either pick the icon for the y equals editor, or usually since people kind of leave their calculator in home screen mode, I'll just show you how to get to the graph area. So you just press little diamond key F1 to get to y equals land. And you'll see here I have my functions that I can graph. So the first function I'm going to enter 5 plus x to the fourth. Hit enter. And then the second function is 5 times 3 to the parentheses 0.2 times x, close parentheses, enter. So I got my two functions there. Now to graph, I just hit little diamond key, F3 graph. You can see on top there it says graph in green. And it'll graph, and there it is right there. There's a little piece. So this is an illustration of the presumed intent of this question, which is to get you to fiddle with windows and figure out how to get what you need on a graph. So the first thing I'm going to try is, I just like to go back to, oh sorry, that's not what I meant to do. I just like to go back to the standard frame because I feel sort of comfortable there. So I'm going to go to zoom standard. As you can see, there are a lot of different options here. Zoom standard just gives me a standard window. And I'm lucky enough to see, okay, it looks like everything I want to see is kind of there, and I just need to zoom in on it, right? So let's see. We got both graphs here. I see some intersections, so I'm gonna pick, say, from -2 to 2 in the x-axis, and then y I'll go from 0 to, well, I know that when x is 0, if you look back at the functions, that they both equal 5. So I'm going to go up to like 10. Alright, so to enter in a window, diamond and F2 window, and now I just enter in the coordinates, right? So I'm going to go from, what was it, -2 to 2, and then y I'll go from 0 to, okay, sure, 10. So once you enter in your coordinates, hit diamond graph again. And I think I get a pretty good idea of what's going on here, right? I see two intersections. One at x equals 0. If you check the equations again, we have 5 plus x to the fourth when x is 0 equals 5. 5 times 3 to the 0.2x when x is 0, that's just 3 to the 0, which is 1, so 5 times 1 is 5. Clearly they intersect at 0, and you can convince yourself that, in fact, there should be two intersections. However, And here's why this is truly an evil question. It turns out that you wouldn't have guessed this from the graph from looking at this. In fact, there are 3 intersections. And the reason is that exponential functions grow faster than any polynomial function when you'd have x, for x large, let's say. As x gets larger and larger, this exponential function will eventually catch up to and pass this polynomial function. But looking at the graph, you would never guess that. So let's look at a bigger window to show why this is truly an evil question. So negative 10, now let me just say negative, all right, negative 10 to 10, 0 to 100. Right? 1, 2 intersections. This is the exponential. This is the polynomial. Normally, if you were on a test, you would look at this and say, oh, okay, I'm done. I mean, look at this. This is never going to cross that, right? Turns out, let's see if I can even get this on a graph. So let me go from negative 30 to 30, 0 to 100. Let me see. Now, of course, I wouldn't expect you to realize this on the test because it requires you to understand something about. So, okay, the graph is not telling us what's going on here, right? You'd have to be extremely lucky to get the right window that will actually show where this intersects this again. In fact, you probably don't even believe me. So I'm going to show you how another technique you can use to find intersections, which is very important, which is the solve function. So to get to solve, I go to home screen mode, press F2, it says algebra for some reason, and the first option there is solve, hit enter, solve. Now I enter an equation that I want to solve, so I'm going to put 5 plus x to the 4th equals 5 times 3 to the 0.2 times x, close parentheses, comma, what variable do I want to solve for? X, close. Now, here's the crazy thing. This should tell us all the values of x for which those are equal. Now, you might see in the bottom here, warning, more solutions may exist. This is because the calculator internally uses a numerical routine to find these solutions, which is actually imperfect. It's not algebraic, and in fact, it can miss solutions. So if we look at the solutions here, we know at 0 they intersect. But look at this. At x equals 70, they have another intersection. So, but the thing that you might notice is that the first intersection, which was, I believe, x equals 2. So let's plug in a few values and see what's going on here. 5 plus x to the 4th. This is the such that button. So if I put 5 plus x to the 4th such that x equals what was the intersection? I can't remember now. Actually, why don't I take a look? So I'm going to go back to Zoom Standard. Yeah, so another way to find an intersection, which is, of course, useful to know, is also, before I get into that, another way to find an intersection is, well, I'll show you in a second, but let me try and get a window around the stuff that I care about. This is another technique you can use. Zoom box is another one of those F2 menu options. Lets you draw a box around the stuff you want, which is very nice if what you want to look at is already on the screen. Okay, so now I've got these two intersections. I want to figure out exactly where this one is. So I hit F5, intersection. First curve, it will pick the first function. Second curve, it will pick the second function. I just hit enter, enter. Lower bound, now I have to pick a point, an x point that is to the left of the intersection I want to look at. Lower bound, hit enter. Upper bound, now I need to pick an x spot that's to the right of the intersection I care about. Hit enter. It'll chug for a while, and then it says intersection XC equals, oh, and I just ruined it. It was 1.07 blah, blah, blah. So, alright, so I was in the process of showing you that the punchline of this whole thing is that, in fact, this function has 3 intersections. And if you didn't happen to pick an absurdly humongous window, or know in advance that exponential functions grow faster than a polynomial, you probably would have given up at 2. Yeah, as you can see, well, let's see what, it said that x is around 70 was the second intersection. Let's go back to home screen mode. Okay, home is here. Now, it says that right around here, there's a third intersection. Let's see how big our window needs to be to take a look at that. So I'll put x equals 70, which is roughly around there. Okay, so that is, right, so if you happen to make your window such that y max was greater than 24 million or so, you might have been able to spot on the graph that there was another intersection. Of course, I can substitute x equals 70 into the other function, and I'll get about the same thing because we're looking at a point, roughly speaking, where they intersect. So again, put in an expression such that, and then such that x equals 70, and it will substitute. Hit enter. Something weird happened. Oh, yeah. Scientific notation. 2.4 times 10 to the 7th, which is roughly the same as that. So basically, the moral of the story is this is an evil question. There are, in fact, 3 intersections. If I had put this on the test and you had said 2, I would have given you full credit, because we have not discussed exponential functions yet. But in fact, there are 3 intersections, and hopefully this has illustrated a few things you can do on the calculator. All right, that's enough for now. Bye, guys.